We already went through that. Answer 1 was D. Answer 2 was B.
Doobie.
As in a star, which is spelled like that. Okay, just to make sure nobody hears you and thinks that you're being inappropriate. Speaking of inappropriate, I had a friend in grade school whose nickname was Doobie. I, being a naive little boy, had no idea what it was until I was told where he got the name.
What's a doobie?
His mother and father were hippies. When he was born, she took him out of the bassinet, all wrapped up in a towel, and said, "He looks like a big doobie." And that's how he got his nickname.
This is fantastic.
Yes.
I don't get it.
I don't get it. Actually, that guy's family was part of the Jim Jones, People's Mission or whatever.
Really?
But they were so poor they didn't have enough money to go to Jamestown, and so they lived and became Adventists instead. Yes, they did not drink the Kool-Aid, which is the origin of that. Now back to astronomy. So radiometric dating of things like, and I talked about potassium, argon dating, or rubidium, strontium dating, or you could use uranium and all of its decay products down to lead. All of those are used for dating purposes. Yes, Satish.
So for the carbon-14, is it that you can't go past 50,000 years, or is it that it's not accurate enough?
You simply can't go beyond there. What you have is, remember, you have the half-life, the time where statistically 1/2 of it should have decayed. The half-life for carbon-14 is 5,730 years, plus or minus about 10. So after 5,000, let's say 6,000 to be round numbers. After 6,000 years, you only have half as much carbon-14. Well, if you go, let's say, 10 half-lives, that means you have 1/2 raised to the 10th remaining. Well, 1/2 raised to the 10th is essentially 1/1000th. So after around 60,000 years, you have about 1/1000th of what you started with. And there's so little of carbon-14 already existing that if you cut that fraction by a factor of 1,000, you don't have a measurable amount. And so that's why it's no longer useful. You can't get a measurement because you just don't have anything you measure. Now, this is off topic for astronomy, but very on topic for this discussion. They're finding that things like dinosaurs that are supposed to have lived, tens of millions of years in the past, have some measurable amount of carbon-14 in them. Which then causes a big, big problem, right? And so there's that. There's also the fact that they have, and this is a much more established at this point, they actually have biological tissues, things like sinews and things in these 60,000-year-old dinosaurs. And to the best of our knowledge, those also shouldn't last more than 50,000 years or so. And so to have them in things that are 50 million years old defies what we know about science. And so there are a couple things that are making creationists really seriously say, that doesn't make sense. We need some kind of answer. We can't just blindly say, sure, when we have evidence that says the traditional radiometric dating measurements couldn't be correct. So it's an area that, at least in my mind, is heating up. In the Richard Dawkins' mind, I'm sure it's not heating up because, his mind is as closed as my mom's. It's just my mom's on the other side of the aisle. Yeah.
I think Richard Dawkins hates Christians. Once wrote in his books something calling Christians ignorant and even wicked.
Yes, he is a very hate-filled man.
Quite ironic that he was a Christian when he was a teenager.
I did not know that. Moving on to question number 3. What comes between the terrestrial planets and the Jovian planets? Now, before we answer, this is something you're going to have on the test, so let's go through the order. What's the terrestrial planet starting from the sun?
Mercury, Venus, Earth, Mars, Jupiter. Whoa.
Okay, so I had Mercury, Venus, Earth, Mars, this thing that we're looking for in our question, Jupiter, Saturn, Uranus, Neptune. It's not a separatrix. It is a mathematical term,
That's
but
actually a thing? Okay.
I was so happy to see that at the quiz.
so what is it?
D.
It's the Oort cloud.
It's the asteroid belt. Not all asteroids are in the asteroid belt. For instance, you have the Trojan asteroids that are before and after Jupiter. They're called the Trojan asteroids because they're kind of hiding in these places called, there's a certain number, there's like 5 Lagrange points, I think. But these Lagrange points are stable places where things can be locked in, and they're locked in there. So you have some that are leading Jupiter, some that are trailing Jupiter. So those are called the Trojan asteroids. So they're not only in that belt, but that's where you find the vast majority of the asteroids, including Ceres, the dwarf planet that's an asteroid. Finally, what element makes up the vast majority of the sun and yet is only a minor component of the Earth? It's hydrogen. It's like 72% by mass, 90-some% by number of atoms. So it doesn't matter which one you measure, that's still the vast majority. Just for the scientific reasoning on why people believe that occurred, in the Big Bang, the scientific theory is the Big Bang started with just a big outpouring of energy, and then as things cooled, you were able to form nuclei, and the first thing you were able to form was the hydrogen nucleus. And then you could merge 2 protons together, and through particle interactions, you could have something like a deuterium, which is a proton and a neutron. Do it again, you could have a tritium, a proton and 2 neutrons, or you could have a helium-3, 2 protons and a neutron. Do it again, you have a helium-4, 2 protons, 2 neutrons. Do it again, you got a problem. There's no stable element, no atom that is stable that has 5 things in the five things in the nucleus. And so you have a big drop-off in anything larger than that because you couldn't just sequentially add things. Keep going, 6, 7, there's also nothing with 8. And so that's another stopper. So in terms of how much we have of the elements, hydrogen and helium is almost exclusively what's believed to have been made in the Big Bang through the nucleosynthesis. Trace amounts of lithium, beryllium, everything else would be in star death. And so that's why you have primarily hydrogen and helium, hydrogen being the first one that's made and the one that's dominant. Okay, that's our quiz. Homework questions, because people said they had questions on homework. What questions do you have? Go ahead, Seth. Seth was all of them. That's a bad sign.
Yeah, well.
I just want to know if the answer that I put down is correct, and if not,
Okay, I'm waiting for Seth because he was the first one to say it. Can you help him?
Yeah, I guess this is kind of an easy question, but I was just confused on number 3 when it's talking about how astronomers know about the chemical and physical properties of stars by their spectra.
Mm-hmm.
I understand how they know chemical properties, like the composition and what stuff is in there.
Yeah.
I am confused as to how I thought temperature might be a physical thing.
Yes,
It is?
that's what I was going to say.
Okay.
Temperature and size are the 2 physical things that they get from the spectra. And let me review this a little bit because it's something that kind of got brushed aside to your personal reading. Temperature, one way of determining temperature is using Wien's law.
Yeah.
Wien's law says that the peak wavelength is equal to 2.9 times 10 to the 6th nanometers times kelvins divided by the temperature. Or switch those 2. So you can find the temperature from knowing what the peak wavelength is. But you have things like atmospheric absorption and whatnot that makes it so it's kind of hard to determine exactly where the peak is. You look at the sun's radiation, you have something that's, like this, where would the peak be on the black body curve? I mean, I can take this and say, okay, well, the highest point in my scribble is right there, but maybe the black body curve, the best fit for the black body curve is going to be something like this, and the peak is actually over here. You've got an uncertainty there. And so instead of using that, what scientists do is they take how strong different absorption bands are. Because if you have something like, let's take hydrogen, the dominant atom in the atmosphere of anything, well, of any star. Hydrogen, if it's cool hydrogen, most of the electrons will be in the lowest energy state possible. So the absorption lines will be strong for absorption from n equals 1 to 2, 3, 4, or 5. You saw that in our Flip Friday activity. If the temperature increases, you have these atoms hitting each other, and the electrons get pushed, they get hit, and they get energy from collisions, and they go to higher levels. So if you get to around 10,000 kelvins, you have a very large percentage of the electrons are actually in the n equals 2 state. So you have much stronger absorption from the Balmer absorption lines than from the Lyman. The Lyman is starting at n equals 1, Balmer starting at n equals 2. You get up to about 20,000 kelvins, and now the electrons have moved out to n equals 3. So the Balmer's weak again, and now it's the Paschen that's going to be stronger. And so they look at the strengths of those, and using not just hydrogen, but using other atoms as well, they can pinpoint what the temperature is by, okay, this is this percent, and this is this percent, and they can use statistics to determine what the temperature has to be. So that's one of the things that they get from the absorption lines, the temperature. A second one, the size. And you might wonder, we haven't even talked about the spectral classes, which is the temperature, or the one that has to do with size. Now I can't remember what its name is. But to determine the size, they actually look at the width of the absorption lines. If you have atoms that are relatively isolated, then the absorption lines are going to be very thin. But if they're having collisions with other things, it's going to broaden the absorption lines. And so they measure how broad those are, and it tells them how thin the gas is in the atmosphere. And very large stars have thin atmospheres. Small stars have thick atmospheres. And so the broader the line, the smaller the star. So that's another thing that they can determine from that. Luminosity class and spectral class. Spectral class is the temperature, luminosity class is the size. So those are two physical properties that they get from it. Okay, I'll entertain one more homework question. One from someone else. What do you want, Cody? What did you want, Eliezer?
Which question do you have? Mine was the second one, number 2. The temperature range droppings. You can only with that one? Okay. That's why I...
Okay, so you said 4, Cody?
Yeah, 4.
Okay, so number 4 is small knots of gas in the Crab Nebula are observed move-ing away from the position of the dead star at its center. And then it gives us some information. So I'm actually going to go to, I'll go to the next slide and just go down to the bottom here. And so let's look at the information they give us. They give us that, okay, we're down here on Earth. We're looking up here. Here's the star at the center. And in 1940, we had this object out here. So that the angle made between that object and us was 150 arc seconds. And then in 1990, it was out here. So that it had moved out an additional 8 to 9 arc seconds. Now, since it's an additional 8 to 9, I'm going to approximate and say 8.5. So I'm going to just take that and say about 8.5 arc seconds. And then they say, okay, using this information, when did it explode?
So you have to calculate the speed.
So first you have to calculate the speed, the rate at which it's expanding. So it expanded 8.5 arc seconds in 50 years. So our rate is equal to 8.5 arc seconds per 50 years. And it had expanded 150 arc seconds prior to 1940. So if I take my 150 arc seconds and divide it by the rate, 8.5 arc seconds per year, per 50 years. That's, remember, when you divide by a fraction, you invert and multiply. So you have something like that. And that gives you a number of years. I actually remember what it is, but I want people to actually do their own work and not just copy down.
A number of years?
Yes, it is an actual number.
I got that.
And so that's how many years prior to 1940 it must have started. So you just take 1940 minus that number of years.
There's going to be a time span though, basing it. If you averaged it, I based
Yeah.
it at 8 and then based it at 9.
Right, and so you're going to get a range, right?
Time span of years.
Yeah. So mine is going to be approximately this time. Yours would be between here and here. Either one is fine.
Okay, that's what I put between such and such.
And so that would give you a year.
My range was 190 year range.
No, my range is approximately 70 years.
And
I did 8 and 10.
the 8.5 comes within 4 years of when the Chinese observed it. So taking that average was pretty good for getting the right number. Of course, they probably kind of fudged the numbers just a little to make sure you get the right number. Okay, now to our material du jour. Temperatures of, now this says temperatures of major elements. This is actually the melting temperature of the elements. Melting is an important part of here that I missed when I made this slide, because yes, I made this myself.
You did pretty good.
Yeah, except for I forgot the word melting.
You did pretty good.
The textbook has a version, Wikipedia has a version, and I made mine from using the two.
The web edition.
Yes, that's right. So you look here and you see hydrogen has a melting temperature or condensation temperature. That condensation is when if I have two, yeah, I was wrong. Melting isn't right. Condensation is a different thing. Condensation is if I have two molecules that fly and come together, they stay together and form a droplet. So for hydrogen, that's 180 kelvins. Now, think about what is 180 kelvins? Hot, cold, room temperature. Cold. Room temperature is around 300 kelvins. So below 300 kelvins is colder than room temperature. Above 300 is warmer, so it gives us a reference point. So hydrogen there, well below room temperature, has to be cold for hydrogen to stick together. Helium, 3 kelvins. Super cold. Carbon, 80 kelvins, very cold. That's in the form of methane. Nitrogen, 130 kelvins. Oxygen, if it's in water, it's pretty cold, but if it's in silicates, that is like in rock, then it's 1,300 kelvins. That's very hot. Keep going down. Neon, very cold. Silicon, once again, silicates to the same temperature. Iron, very hot. Why are these important? We're looking at this in the context of how the solar system formed. And one of the things that our model had to explain was why we have significantly different planets in the inner portion than the outer portion. That was something you had to conjecture on your Flip Friday. And so here is the scientific answer. Things that are closer to the sun were receiving a lot more radiation from the sun. They were much hotter. And so only things that have high temperatures for condensation would actually stick together and start forming clumps. And so you had lots of gases here in the region close to the sun, but only those elements that I put in red, and you'll find this funny. In last year's lecture, I had 2 different versions of this chart, and the first one that I was in there didn't have the colors, and I was like, oh, I should totally color code these. So I went through and changed all the colors, and then like 3 slides later, I had the second version. I had a before and after clicker question with them all color coded. Anyway, I know you don't care, but I was like, that's a waste of time. So because of the high temperatures where they condense, turns out that we have these are the primary elements for the Earth. Even though all of them would have been present at the time the Earth was formed, and in fact, the hydrogen and helium would have been much more common. So you can see for the sun's mass, the hydrogen and helium combined is virtually 100%, well, 98% or so of the mass in the sun. But for the Earth, you combine those two, and you're, 0.003% of the Earth's mass in those same elements, because they couldn't clump together. Yeah.
So it says that in the Bible that the sun was made on
The fourth day.
How are we having the Earth after the sun? We had the sun was made after the Earth.
Okay.
Light was made before the sun was.
Yeah. If you, and you probably know I teach origins as well. If you talk about the creation story from Genesis, we have a very simple day 1, creation of light. Day 2, you have the separation of dry land, or of water on earth, water above. Day 3, separation of dry land from the oceans, as well as the creation of some vegetation. And then day 4, we have the sun to rule the day and the lesser light to rule the night. And so you have some weird questions like, the evening and morning were the first day. That's the English translation for the end of each day. Day 1, evening and morning was the first day. Day 2, evening and morning was the second day. How do you have an evening and a morning without the sun? Now there's a very common answer that says the evening and mornings for the first 3 days were simply measured by God's presence. God is a light bringer, so when God came, that was the morning. And when God left, that was the evening. That's one answer. Another answer is that perchance, as Moses is seeing this displayed and writing down what he's seeing, he saw light and dark, but didn't see any stars or the sun. But he still said, it's light, dark, so we have evening and morning. And thus, we had, the sun could have been there, and he was just seeing the light. In fact, this is my belief. My belief is that on the first day, before that, the atmosphere of the earth was so thick that you just couldn't see any light. And the first thing God did was he came and just get rid of that stuff so we can see light through the atmosphere, but it's like looking through a clouded window. Like if you go look at Amy Yett's office, she now has frosted windows.
Yeah.
And it was like that, so you can't actually see the sun, but you can see the light. And then we have the next few days are further separation of water. And then on day 4, okay, now that we've done all this other work, now let's clear the atmosphere one last time so we can actually see through it. Now remember, we can only see through the atmosphere in the visible range and the radial range. And so that was where he made another change so we could see through the visible range. And thus, suddenly Moses sees, hey, look, there's the sun and the moon and so on. So there are different ways of interpreting it. And if you're going to take the Bible seriously like I do, you have to do some thinking here, because if you don't do any thinking, you just say, that's contradictory, and there's a knee-jerk reaction, it's contradictory, let's punt the whole thing. And I don't want to do that. Which is why I spent time in my astronomy class to explain how that works. So remember, I said I actually believe the earth is very old, the sun is very old. I do not believe that the creation story in Genesis is from super old. I don't think it was 6,000 years ago, but I also don't think it was super old. And I think that Moses was shown what God was doing then. One last thing on this. Remember, the Bible does say, in the beginning the earth was
Without formless.
Yeah. It was void and without form. So when we start the creation story, I mean, in the beginning, God created the heavens and the earth, but the earth was void and without form, and then he came and terraformed the earth and made it so life could be here.
And there was already water already.
Yes. At the time of the creation of the Garden of Eden. And I mean, there are lots of other beliefs about creation and matching things up, but I gave you a couple. Did I answer your question? Mm-hmm. Okay. So, inner planets, warm temperature, primarily these red things. Outer planets, beyond that ice line, it was cooler. You could have the other things also condense and clump together. And so those formed, and because there's so much more of the hydrogen helium, you basically have a lot more stuff you can make the planet out of. They grow a lot more. So that's the scientific model that holds together. Okay, first of our clicker questions. Got to get back. Don't answer. Well, you could answer now, but it wouldn't take it. If you answer starting now, it will take it. Nobody has. There. Yes, remember is select the 3, so you select 3 and hit enter. When Megan, our first answer,
Earth's
punched
crust.
it in, all of a sudden 3 popped up, and I was like, where? Oh yeah.
Is it Earth's crust, Earth's atmosphere?
You know, crust or Earth itself, not the atmosphere.
Okay, because it just had Earth apostrophe S.
Yeah. Yeah, because if you use the Earth's atmosphere,
Then you're gonna.
your answers are D, E, and I don't know.
So it's Earth's crust.
Yeah. Do you have your clicker, Satish?
Yeah, I should have selected mine.
Did you hit enter? There you did. Yep. All right. So we have 2, 2, 6, 1, 9, 1, 8, 10. Well, the top 3 vote getters are these 3. There's a fair number that said carbon. If we were to go back to the previous slide, we would see the 3 in red, oxygen, silicon, and iron, are by far the most common. Carbon is indeed the next one, but that's a very small percentage compared to those 3. So our answers were these 3, and why is it those 3? Okay, anybody have a correct answer? Satish.
Is it because it's our Earth's surface is different in the sense like you have solid surface?
Well, we have a solid surface because of why we have those. What were you going to say?
They are able to condense in
Yes.
Oh.
Those are the ones that can condense at the high temperatures. That's why they became the dominant ones here on our crust. Okay. On to content slide number 2. This is just talking about condensation. When you see steam, you're seeing water vapor that's condensed. I am going to just move beyond that because I've talked about condensation enough and we're low in time. So here is put together then the story of how scientists believe the solar system formed. Started with that solar nebula, the big cloud of gas. Shock wave comes, causes it to condense a little, But when it condenses a little, gravity gets stronger. So then gravity pulls it in. As it pulls it in, because of just random rotations, the average is 0 and it starts spinning faster. That spinning faster makes things collide with each other and equal out to get basically circular orbits in a flat plane. Then we have clumps that form, and those clumps that form are called planetesimals. Now you have terms like protoplanet and planetesimal. Right now I'm not going to be concerned about the difference in those two terms. But you have these little planetesimals, the little seeds of a planet, and as things hit them, they can grow, their gravity gets stronger, they can pull more in, and so they form centers of mass that might someday become a planet if they don't collide with something and get obliterated. So the theory, for instance, on what created that asteroid belt is that a planetesimal that was somewhere between the orbit of Mars and the orbit of Jupiter got torn up either by a collision or simply by the tidal gravity of Jupiter and broken into all of these pieces to make the asteroid belt. And in fact, we believe that there should have been lots of impacts early on. This is a fairly logical idea. If you have millions of pieces of debris all flying around, you're going to have lots of things hitting you. But every time something hits you and sticks, that's one less piece of debris that can hit you in the future. So the amount of debris drops over time, and thus the impacts drop over time. So the impacts should be much, much more rare now than they were in the past. Do we still have objects hitting the Earth? Yeah, we do. You might remember just, 2 or 3 years ago, there was some excitement in Russia where they had a thing that came over and a big bright light in the sky and knocked people around. It was what?
Did that happen in 1904?
That happened.
No, I'm talking about that happened in like 2013 or so, 2014, something like 2012 or 13, something in that ballpark.
You can watch it on YouTube. People used to have. They still do.
Yeah, people had smartphones.
No, they had their in Russia and those places they have dash cams on their cars all the time. Yeah, you know
But
what I'm talking about.
yeah, and yeah, so yes, we do still get impacted. And in fact, small stuff impacts the Earth's atmosphere all the time, but burns up. Larger things, we still have, I think it's something the size of a house or bigger hits the Earth's atmosphere about once a month. So we're still getting bombarded by things, but not really big destructive things. If a really big destructive thing hits us, well, that could be bad. And that's why you go to somewhere like space weather, and you'll see a listing of near-Earth objects, NEOs. Things that are going to come close. And every now and then we have one that comes 1/5 of the distance from the Earth to the Moon. Now to me that's kind of scary close. But usually things that come that close are about a meter or two across. So if it actually hits the Earth's atmosphere, it's going to be destroyed in the atmosphere. We don't care. Oftentimes they don't find them until after they've passed. Because they're small, they're not obvious. After it whizzes by, they're like, hey, what was that? Okay, so we still have impacts, but not nearly as much. If you look at the moon's surface, you see lots of impact craters. Very visible. If you look at Mercury's surface, it looks just like the moon. Lots of impact craters. If you look at the Earth's surface, we do have a few impact craters. There is the Barringer Meteor Crater down there in Flagstaff, Arizona. There are a number of other craters. The one that was found in the last 20 years that's very famous is the Chicxulub one down there in Yucatan.
Witches of the water.
Yeah. And it wasn't discovered until recently because there's just not much there. Why? Because on the Earth we have an atmosphere and we have water on the surface. And the water in the atmosphere cause a lot of weathering, which is breaking up of the soil, and erosion, which is transportation of that broken up soil. And so it cleans up the evidence of the impacts. Whereas on the moon or Mercury, don't have atmosphere or liquid water, and so you don't have anything cleaning it up, and you can see very old impacts.
See what happens to Venus?
Um,
Its atmosphere being the way that it is. Did he just never?
It clearly has impact craters because it has a dry atmosphere. So, without the water, it takes away a lot of the action. But you're also going to have things like winds that would kind of obliterate, the finer details. I'm speaking off the top of my head, of course. Never sat down, and one of the great things about students asking questions is it makes you think about things that didn't come to your mind.
That's what we're here for.
Yes, to educate me.
My degree.
Okay, steps in planet formation. I'm not sure that our textbook has a great discussion on this, but in going from being a planetesimal to a protoplanet to a planet, there are 4 major steps. And so step number 1 is differentiation. Differentiation is where you have a separation of materials by density. More dense things sink to the center, less dense things float outward. So when a planet initially formed, you would have your dense things like iron mixed with your less dense things like clay. Just throw in a little, Tower of Babel statue from Daniel's time.
Daniel's dream.
Yeah. But differentiation, the things have to be somewhat fluid for that to occur, so it occurs early on when the planet's very hot because of all of the energy of the stuff coming together. You have the more dense stuff like iron and nickel sink down to form the center of the planet. The less dense things like rock float up to the surface. And so now we have our differentiated Earth because that was our first step of planet formation, differentiation. Now after differentiation, we have flooding. Flooding actually has 2 pieces to it. First, the obvious one. We usually think of flooding as flooding by water. That's one of the pieces of flooding. But another piece of the flooding is flooding with melted rock. Melted rock is called magma. When it's below the surface, it comes up in a volcano, we call it lava. That molten rock would flow over the surface, giving us a fairly smooth surface in the early days of the Earth. And then if it cooled and you had the right conditions, you could also have water flooding over the surface. After you've had this flooding, then we start worried about things like the atmosphere. It is believed that the Earth is on its 3rd atmosphere. First atmosphere would be an atmosphere made of the gases that were common at the time that the Earth was formed. So the gases that were common in the solar nebula. We can look at the sun to get an idea. What's the most common gas in the sun? Hydrogen. Next? Helium. So that primary atmosphere, the first atmosphere of the Earth, should have been primarily hydrogen and helium. But the Earth doesn't have a high enough gravity to hold on to hydrogen and helium. Their velocities are higher than escape velocity for Earth, and so they were lost. So we lost our first atmosphere. So then we have a secondary atmosphere. You have very hot rocks. Hot rocks will bake out whatever gases are in the rocks. And so the secondary atmosphere would be gases that were baked out of rocks. And then you say, okay, so why is that not the current atmosphere?
Because comets.
Because comets. Yes, yeah, does it say that up there? Yeah. You see the secondary gases in the picture top right, and the picture bottom right, you have the comets. Comets are made up of things like water ice, ammonia ice, methane ice, and nitrogen ice. These things come and hit the Earth and deposit their gases, and that's what gives us our tertiary atmosphere. This is believed to be the atmosphere we're in now. So the Earth's atmosphere has gone through some interesting changes, according to the scientific model. Who was there to record this? Yeah, no human at the very least. So this is all based on scientific modeling. We can't test to see if that's what happened, but what we can do is we can calculate what would happen with what we understand, run computer models, simulations, and say, yeah, that seems right. If we could see lots of planets nearby, we could test predictions of our models against those planets. We are not to that stage in planet identification yet.
All we would need is for that giant volcano on Mars to go off and then hit it with some comments and we're good to go. Right?
Good thinking, but yeah. Okay, let's answer this clicker question here. How can the solar nebula theory be tested?
We can't. Oh, oops. Just one?
Yeah, I believe this is just one. Doesn't mean there's only one right answer. It's just answer one.
It's giving me options.
Is it more than one?
Yeah.
Oh, okay. I'm wrong then.
Oh, answer more than one?
So answer as many as you like and hit enter. As many as you think are correct. Cody's got this down. Okay, we've all answered. We had 8, 2, 8, 9. So only 2 people thought that it would be reasonable to create a new solar system. I'm with the rest of the class. That's not a very reasonable option. I mean, yeah, in theory, if we could do it, that would work. But that's not very reasonable. 8 people said it can't be tested. If it can't be tested, it's by definition not scientific. That's why a belief that God did X, Y, Z, God created the earth, is not scientific because we can't test God creating the earth. Not being scientific doesn't mean it's not correct, but it's important to understand why people say, creation isn't a scientific argument. It's not. It's not a statement about its validity. Okay, so it can't be tested. It can't be tested completely, but you can determine what predictions of our theory make and then look for situations that would show if that's right. And that's actually how something like an evolutionary model is tested as well. You make predictions, well, life could occur from this, this, this. An example for evolutionary, for abiogenesis, for creating life from no life, is that if you have the right chemicals and you have the right conditions like an arc, something for energy, you can form certain amino acids, things that are necessary for life. It's not life, but things that are necessary for life. And so they say, okay, we tested this part, it's possible. And then they say, okay, so we're going to test all these different parts. Still a lot missing, but that's how it's tested. Okay, the last one, testing by computer modeling. Once again, that's not a strong testing, but that's saying it looks like the predictions should do this. All right, have a great long weekend. Remember, there is homework due tonight. Huh? The homework, you already did it. Yeah, just
What if you already turn it online?
that's fine.
And no Flip Friday?
Correct.
No school